Hello, it's Dumplet here. Here's an item on number theory. Find all natural n such that n divides a raised to 25 minus a for all natural a. Credits to the Art of Problem Solving community for this item. Now, let's try to dissect this question a little bit further. We're asked to get the possible values of n such that n divides 1 raised to 25 minus 1, n divides 2 raised to 25 minus 2, n divides 3 raised to 25 minus 3, and so on. So that's the thing that we have to take note here. Now, we can try to think of finding the largest possible value of n first, because since we're talking about divisibility here, if n works, then any smaller divisor of n works. Just because if n divides all of these, then it is pretty obvious enough that any divisor of n will also divide all of these. So we can just try to get the largest possible value of n, and then if I want to get all the other possible values, I'll just get the divisors of n. So let's try to set the GCD of 1 raised to 25 minus 1, 2 raised to 25 minus 2, and so on to be equal to n. Now, the GCD of this infinite set of numbers, that's going to be equal to the largest possible value of n, because that is as per the definition of, as per the given. So, but then again, we cannot directly get the GCD of an infinite set of numbers. So what we can do is at least create a bound or an upper bound for at least what we can to get the maximum possible value of n. So we're going to make the following claim. So claim 1, the maximum possible value of n is less than or equal to 2,730. So as I mentioned a while ago, we cannot really get the GCD of an infinite set of numbers. So let's just focus on this. Now I'm using 2 raised to 25 minus 2 and 3 raised to 25 minus 3 because 1 raised to 25 minus 1, that's 0. So it doesn't really help us in any way. So let's just focus on this instead. We have 2 raised to 25 minus 2 and 3 raised to 25 minus 3. They're all in the same format of following the format of x raised to 25 minus x. So we can try to deal with this first, and then, although it's going to be long, we can try to use factoring, because x raised to 25 minus x, I can factor the x out in the first step. So first step, I'm going to factor the x out. In the second step, I'm going to factor x raised to 24 minus 1 via the sum and the difference. I'm going to factor x to the 12 minus 1 into this, as you can see in the blue braces here. And then we can just continue factoring into the final form, or at least currently it's going to be this. So it's just using using our formulas in, or our knowledge in factoring, we can reach from x raised to 25 minus x into factors of a lot of these. So we can try to use this to at least get some of the common factors of 3 raised to 25 minus 3 and 2 raised to 25 minus 2. So using this thing above, we can factor into this and this. Now, we can try to deal with the smaller expressions. I deliberately didn't factor these two yet, 2 raised to 12 plus 1 and 3 raised to 12 plus 1, because of the following point that I will be making. Now, I'm taking a lot of shortcuts here, but this is technically some of the factors, the incomplete factored form of 2 raised to 25 minus 2. And here we have the incomplete factored form of 3 raised to 25 minus 3. But the necessary details, at least the essential details, are there, because we can try to get the GCD so far, at least the common factor that we know, or at least we have a lower bound for the GCD of these two numbers. Now, they both have a 2, and I can conclude here that 2 will be the largest power here, because aside from the 2 here, none of the other terms here are even. So there can only be 2 raised to 1 in the final GCD of these two numbers. Same can be said for 3, because apart from this 3, there are no other 3's present here. We can obviously check this modulo 3, and that's going to be 1 modulo 3. So there's only 1 3 here. Well, there's 3 squared here, so we can conclude that there is a GCD of 3, but the largest power of 3 becoming the GCD is just 3 raised to 1. We can try to check 5. Same thing. There's only 1 5 here, and there's no 5 here in 2 raised to 12 plus 1. You can work it out. You're going to get that 2 raised to 12 plus 1 under modulo 5, that's going to be equal to just 2. So you'll not be getting anything here. So we have the 2 5's here to be common. So we're sure that in the GCD of these two, the power of 2 is 1, the power of 3 is 1, and the power of 5 is 1. Next, we can focus on the next prime number, 7. Same reasoning. The 7 here and the 7 here, there are no other 7s here nor here. You can try to check it out. In fact, both of them are 2 modulo 7. You can try to work it out yourself. Both of them are 2 modulo 7, and you can use Fermat's little theorem to help you along the way. So we know that the GCD so far is going to involve 7 raised to 1. And then lastly, the prime factor of 13. Again, there's only one 13s here, and there are no other 13s here. Both of them are 2 modulo 13. Again, you can use Fermat's little theorem to verify that. So GCD so far is just this. And, well, there is a 73 here, but you can easily verify that 4097 is not divisible by 73. So we have the GCD so far to be this. And it can be concluded from here that if this is the lower bound for our GCD of, or at least for this value, the lower bound. So we know that this is greater than or equal to 2 raised to 1, 3 raised to 1, or just 2 times 3 times 5 times 7 times 13. And should it go more than this, it's going to increase because there is a common factor between 2 raised to 12 plus 1 and 3 raised to 12 plus 1. And this is the thing that we want to check. So let's try to check if there are any other factors that are common to 2 raised to 12 plus 1 and 3 raised to 12 plus 1, because that's it suffices us to check for the GCD of these two. So let's try to get the GCD of these two numbers. Now, I can do the following step. That's by Euclidean algorithm. So you can check this card if you're not really familiar on what the Euclidean algorithm is. Basically, you can just take the GCD of two numbers by taking the GCD of one number with its difference. So like from 3 raised to 12 plus 1, I just subtracted 2 raised to 12 plus 1 to end up at 3 raised to 12 minus 2 raised to 12. Now the reason why I wanted to do that, because, well, I can directly factor these two, but I figured that this form, 3 raised to 12 minus 2 raised to 12, it's easily factorable. As you can see, there's a lot of cubes and squares that you can factor using just the difference of cubes, difference of squares trick. So I've done the work here, and this is the result. So initially we can factor into this, and then we can just keep factoring to these 4 terms. And I also did the simplification of the factors. Now, they're all prime numbers. You can verify that. 17 is prime, 241 is prime, 19 is prime, 5 is prime, 7 is prime, 13 is prime, 61 is prime. And we can already tell no 2 prime numbers are the same here. So the GCD of this and this is actually just 1. So if I go back, since the GCD of these 2 numbers is just 1, and the GCD so far is this, we can already conclude that the GCD of 2 raised to 25 minus 2 and 3 raised to 25 minus 3, we can take the equality case now since we're sure of it. So the GCD of 2 raised to 25 minus 2 and 3 raised to 25 minus 3, that's just 2,730. Therefore, our claim that the maximum possible value of n, we have an upper bound for it, which is 2,730. So logically, in like mathematical proofs, you might want to try out some values of n and take a look at the following claim. I claim that the maximum possible value of n is indeed 2,730. So if I can manage to prove that n can be 2,730, then that's definitely going to be the maximum. Because from my claim 1, we've proven that the upper bound for the maximum possible value of n, the upper bound of n, technically, the upper bound of n is 2,730. And if I can prove that 2,730 is true, then I'm done. So let's try to take a raised to 25 minus a mod 2,730. Again, a is a natural number, so we cannot really assume anything. Well, I can factor a, that's possible, but there's something that I have to do, and it's hidden inside this box, and it's actually this. The thing that we've been using to verify all of our stuff, Fermat's little theorem. So what do we do with this? Because we know that, how do we get 2,730 in the first place? It's just a product of a lot of primes. So 2 times 3 times 5 times 7 times 13. Let me just rewrite it here. So 2,730, that's just 2 times 3 times 5 times 7 times 13. So we can try to take mod 2, mod 3, mod 5, mod 7, and mod 13. Now, mod 2, let's try to take mod 2. That's obviously 0, because if A is odd, then this is going to be even for sure. Then if A is even, then we're done. So we can conclude that A raised to 25 minus A, or equivalent to this, under mod 2, so it's going to be 0. So under mod 2 is equal to 0. So let's just remember it for now. Now let's try to check under mod 3. Now under mod 3, we can try to take two cases here. If A is a multiple of 3, then we're done, because it's going to be 0. But if A is not a multiple of 3, then by Fermat's-Little theorem, we're going to have A squared is congruent to 1 modulo P. Sorry, 1 modulo 3. This is by Fermat's-Little theorem. Now, A raised to 24, that's just A squared raised to 12. So A raised to 24, it's just 1 modulo 3. We're just going to effectively get 1 minus 1 here. So whether A is a multiple of 3 or not, the answer is 0. So we can conclude that A raised to 25 minus A under mod 3, that's equal to 0. Now we can see here that if you want to prove that it's true for under mod 2530, I have to prove that it's 0 mod 2, 0 mod 3, 0 mod 5, 0 mod 7, and 0 mod 13. Why? And why will that suffice? It's because of the Chinese remainder theorem. I have 5 modulos, or I have 5 congruences under 5 prime numbers, so I can get a unique modulo system, or a modulo residue, under mod of their product, which is, in this case, 2730. So you can try to prove it now for mod 5. Now, again, we're going to take two cases. A is a multiple of 5, then we're done. It's 0. If A is not a multiple of 5, then we can use Fermat's-Little theorem here to say that A raised to 4 is 1 mod P. So 1 mod 5 in this case. So again, A raised to 24, it's just A to the 4th raised to the 6th power. So it's just 1 anyway, so 1 minus 1, effectively 1 minus 1, so it's 0 modulo 5. Same can be said if you try to take mod 7, because again, we take two cases. A is a multiple of 7, we're done. If A is not a multiple of 7, then by Fermat's-Little theorem, A raised to 6 is congruent to 1 modulo P, which is in this case 7. Again, A raised to 24, that's A to the 6th power raised to 4. So effectively, we're doing 1 minus 1. So indeed, that's going to be 0. So under modulo 7, it's still going to be 0. So you can try to see the thing here that we're trying to prove. And lastly, mod 13, again, if A is a multiple of 13, then we're done. But if A is not a multiple of 13, then we have to use Fermat's-Little theorem. So A raised to 12, that's 1 modulo P. In this case, it's 13. So again, A raised to 24, it's just A raised to 12 raised to 2. So it's still 1. So 1 minus 1, effectively, is just going to be 0 as well. So we've successfully proven that under modulo 2, modulo 3, modulo 5, modulo 7, modulo 13, it's A raised to 25 minus A, this expression over here, is congruent to 0 modulo all of them. So we're done. It's going to be divisible by 2730 for all natural A. Again, we didn't really consider any special cases here. So we're done. Indeed, the maximum possible value of n is 2730. And going back to what we discussed a while ago, since the maximum possible value of n is 2730, then all natural numbers n that divides 2730 will work. Just take note here that we're going to additionally state that n is natural. So n is a natural number. So it's a pretty long video, but hopefully you guys learned something new from this video. Hopefully you guys like this video, and I'll see you in the next one. Bye bye.